we're going to talk about precipitation reactions. So you've probably heard water referred to as being hard. What they mean by that is that the water has calcium and magnesium ions dissolved in it. Soft water does not have a lot of ions dissolved in it. And the reason we care is because calcium and magnesium ions can react with soap molecules and form this scum. It's like they call it a gray curd. That's your bathtub ring, right? So you take a bath, the tub was nice and clean when you got in there, and you get out and the water drains away and there's like this gray ring around the bathtub and you're like, was I really that dirty? Gross. No, that's not dirt from your body. That's the hard water reacting with the soap that you used to clean yourself. And so, you just have to get rid of it and clean it off. Laundry detergent has sodium carbonate in it because you don't want this curdy stuff to be forming on your clothing, right? So laundry detergents add sodium carbonate. Sodium carbonate reacts with calcium. The carbonate reacts with calcium to form calcium carbonate, which is not soluble. And magnesium carbonate is not soluble either. And so those are said to precipitate. So precipitation is like when rain falls from the sky. Did you guys see rain on Saturday? It was like just enough to really mess up your car, right? Just like make it look really, really bad. Precipitation is something that falls from the sky. So when you put certain chemicals together, they can form a precipitate. Remember experiment 2A? And you added things and it formed a blue solid and then it formed a black solid and it fell down to the bottom, right? Like weird black snow. So calcium and carbonate will react with each other and form an insoluble compound. So carbonate has taken all the calcium ions out of the water, so there's none of them left to make the soap scum. And magnesium gets taken out by carbonate also. And so the sodium carbonate essentially is softening your water so that it doesn't make that gray, dingy stuff all over your white shirts. So a precipitation reaction is defined here. We get a solid, which is called the precipitate, that forms when we mix two solutions. So you mix two solutions. They don't need to be colorless, but they will be clear. You can see through them like water or apple juice. You mix them together and you see something cloudy happening. That is a solid forming. So in this example, we have potassium iodide solution and lead nitrate solution. And when you mix those together, what happens is the lead ions and the iodide ions are going to form an insoluble compound because lead 2 is one of the exceptions for chloride, bromide, and iodide. And so that will form a solid and sink to the bottom, and then the potassium and the nitrate are going to be left in solution. Any questions? We're going to learn how to predict whether precipitation will occur or not. So what we're doing is we're looking at the original compounds. And here, I've mentioned, I think of the metals as being masculine and the non-metals being non-masculine or feminine, right? And so this is, let's go back to the 1950s. And here we've got potassium and iodide are going to a party. Guy, girl, they're going to a party. So they come in their beaker. And lead and nitrate are also going to this party. They come in their beaker. And potassium and iodide are friends, but they're not like really stuck on each other, right? They're just like, well, I didn't want to go by myself. Same thing for these two. Okay, so we get to the party. Now all the ions are in the party house, right? And lead sees iodide, and there's chemistry. And lead and iodide really, really like each other. And so those are the people you find out later on the back porch. They've been necking all night, right? They're not mingling anymore. They're out of circulation, right? Why? Because they really, really like each other. Why do they really, really like each other? Who knows? They just do, right? So what happens to potassium and nitrate? Well, they're just, circulating around, having fun at the party. Does that make sense? So when we are predicting whether a precipitation reaction will occur, we're going to look at the cations and the anions that are coming to the party, and we're going to try swapping partners. Potassium came with iodide. They weren't a thing because they did not precipitate. They were dissolved. So we're going to see if potassium would like lead state, and we're going to see if lead likes potassium state, right? So essentially we're swapping ion partners, and then we're going to see what happens. Sometimes nothing happens. The solutions mix. Nobody gets into a relationship. They had fun, but, nobody got into a relationship. Why? Because the particular people at that party just didn't like each other that much in that way, right? And so this is not a chemical reaction then. There is a change that has occurred, but it's a physical change. It's just mixing. We've mixed the solutions, but no new compound has formed. It's the same ions that were there before. It's now they're just all in the same beaker. So only when we form insoluble compounds will there be precipitates. How do we know if that compound that we're predicting is insoluble or not? We go to the rules for solubility. So these are steps for writing equations for precipitation reactions. Start by writing the formulas for the two reactants, and below that, write the formulas of the products that could form from those reactants. Refer to the solubility rules to see if any of those possible products are insoluble. If they are all soluble, you just get to write no reaction and you're done. And that's what we all hope for. And there will be some that you just get no reaction and you're done. But a lot of them, there will be something. So if any of the products are insoluble, then you need to write the formulas for all the products. And you use S for the ones that are insoluble. Remember, S doesn't stand for soluble. It stands for solid. It's a solid. It doesn't dissolve. And AQ is aqueous. It does dissolve. And then you balance the equation. So let's do some examples. We'll get a little nomenclature practice in here too. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate mix. So they're giving us the names of the compounds. How do we write, I'm all choked up about that. How do we write formulas for ionic compounds? What do we need to start with? We need to start with the ions, right? So ammonium chloride, that's an ammonium ion and a chloride ion. And so we need to know the formula for ammonium, NH4+, and the formula for chloride, which, is why we covered this in an earlier chapter, because we're going to need to know this now. So if those make a compound, what ratio of ions do we need to make a neutral compound from ammonium and chloride? Just one of each, right? This one's +1, that one's -1. So NH4Cl. It doesn't specifically say it in this prompt, but we can assume that these are solutions. And if we look at the solubility rules, of course, ammonium is going to be soluble. So then we have iron 3 and nitrate. Well, iron is Fe, and what does the Roman numeral 3 tell us? Tells us the charge, 3+. And nitrate, we should be able to guess at least that it's nitrogen and oxygen, and there's some sort of a negative charge, right? That's NO3 with a -1 charge. So then we can look at the relative charges. You can do the crisscross thing. You can draw pictures, whatever works for your brain. And we should all come up with the same answer, that we need 1 iron and 3 nitrate ions. And that will also be aqueous. I really like to write these out under the equation that I'm writing, because they're going to come in really handy now. We're just going to see about swapping partners. So we're going to see if ammonium and nitrate like each other. And we're going to see if iron and chloride like each other. Okay? So I'm going to put those two together. Remember, it's always the positive ion and the negative ion, just because. And it has to be a positive and a negative, because otherwise it can't form a neutral compound, and it will not make a compound. So bring the iron over there. And bring the chloride over here. Now, you can't drag on your paper. I just did because it's really fun. But you just copy them down. Does it matter if I put ammonium and nitrate first? What if I put iron 3 and chloride first? That would be fine. Because this is like adding. 1 plus 2 is 3. 2 plus 1, also 3. The order doesn't matter. So to put ammonium and nitrate together to make a compound, is that going to be soluble or insoluble? That's soluble, because ammonium is the first line, always soluble. So this one's going to be aqueous. And what about this one? Also soluble, because we go ammonium and the next line is nitrate and acetate, and then we get chloride, bromide, and iodide. And iron is not one of the exceptions. So this is also soluble. So does a precipitation reaction occur? No, it's just mixing. And so we can write no reaction, or if that wasn't short enough, a lot of times NR, no reaction. Any questions?
If a reaction does form, and like we're writing out the equation, do you have to balance it as well, or just put what the products are?
We have to balance it, yeah. The ionic equations usually balance up pretty easily. It's the ones with like combustion, and some of the redox ones are really nasty. But these guys will balance up pretty easily. Let's do another one. Write an equation for the precipitation reaction that occurs if any when sodium hydroxide and copper 2 bromide mix. So, sodium hydroxide. So the sodium ion and the hydroxide ion. And this is why I wanted you to memorize these, because if you have to go look all of them up every time, it's going to take forever, right? It's just going to be faster. So there's sodium and hydroxide, copper 2 bromide. Again, that Roman numeral tells me what the charge is, so convenient. And then bromide. If you are a bit iffy still on predicting charges and writing formulas and stuff, please come talk to me, because obviously it's not going away. We're not done with that. There's going to be more of it. So putting these together, sodium and hydroxide, one of each. And that one's aqueous. And then copper and bromide. We need 2 bromides to balance the charge on the copper. That one's also aqueous. To predict the products, we're going to swap partners. I'll draw them this time. So I'm going to try sodium with bromide, and I'm going to try copper with hydroxide. Go check out whether they're soluble or not before you start writing all the formulas, because if there's no reaction, then you don't have to do it. Is sodium and bromine together soluble? Yeah, because sodium's in the first line. Sodium compounds are always soluble. Copper 2 and hydroxide. Now, you look through that list, copper's not in there. But you start at the top and you move your way down, you get to hydroxide in the bottom half, right? Hydroxides are generally insoluble except with, right? So this is not one of the exceptions, so this one's a solid. So that means we do have to finish it. So we're going to write the formula for sodium bromide, putting those together based on the relative charges, a plus, and then I'm going to leave some space in case I need a coefficient there. Cu, and I need 2 OHs, and that's going to be a solid. So to balance it, hydroxide here is a polyatomic ion. Nothing happened to hydroxide. She just switched partners and found the love of her life, right? She found copper, and they're going to go off together and be together forever. So we don't need to look at oxygen and hydrogen separately. We're just going to look at that as a unit. So here I have 1 sodium, and over there I have 1 sodium. So far, so good. Here I have 1 hydroxide, and here I have how many hydroxides? 2. So you can't take things away. You can only add things. So that means I need 2 of this guy, right? So I'm going to make this be 2 sodium hydroxides. Now, does that mess up sodium? Yeah, it does. Sodium was fine, and now we messed it up, so we have to fix it. I have 2 sodiums now. Over here, there's just 1. So I need to put a 2 there. So I have 2 sodiums. So we got this guy taken care of. We go over here, 1 copper, and how many coppers over here? 1. How many bromides? And how many bromides? 2. So it'll kind of take care of itself at the end. And there's your balanced chemical equation. Questions? It gets much easier with practice.